Let's give ourselves a fun little mathematical puzzle to think about. We're going to take a simple right triangle, and we're going to build a box using this triangle, using 4 copies of it. And here's how we're going to do it. We're going to take this triangle in its original form, and we're going to lay a copy of it next to it. But this copy is going to be turned on its side, and we're going to line up the edges so that they make a single line. So we have a right angle there. And then next, we're going to take this and we're going to flip it upside down, and we're going to draw that copy of it like this. And then we're going to turn this 90 more degrees this way, so that the final copy of the triangle gets drawn like this. What we've done is created a very interesting looking box using 4 copies of a right triangle. We know that these are all right angles because this is a right angle, and all we did was rotate this triangle. Furthermore, we know more things about this triangle. Let's call this length A and this length B. Since these were all copies of the same triangle again, we can fill in the lengths like this. Call the longer side A and the shorter side B. So what we have is a box where each side was made by joining the sides A and B into a single line. So all 4 sides of this box have the same length. And at the same time, all 4 corners of this box are right angles. This is the definition of a square. So this outer box, let's call this outer box S1 for square, because we know it is a square. What about this inner box? What do we know about it? Well, let's go a little bit deeper into this triangle. Let's label this angle that's opposite from side A, alpha. Let's label the angle opposite from side B, beta. Now we know that the interior angles of a triangle have to add up to 180 degrees. So we know that alpha plus beta plus this angle that we know is 90 must equal 180 degrees. Well, let's just subtract 90 from both sides, and we have alpha plus beta is equal to 90 degrees. Okay, we can use that. Let's zoom in a little deeper to what's happening at this corner right here. We can draw that out on this side. Here's alpha, and since this angle is opposite to side B, it must be beta, alpha. Now we know that if I'm facing this way, and I turn around so that I'm facing in the exact opposite direction, that is the definition of a 180 degree rotation. So this whole angle right here must be 180 degrees. So we have, let's call this angle finally our third angle, gamma. We have that alpha plus beta plus gamma must equal 180 degrees. But at the same time, we also know that alpha plus beta is 90. So really, gamma plus 90 is equal to 180, which ultimately tells us that gamma is a 90 degree angle when we just subtract 90 from both sides. So this inner box has a right angle here. And since we have the same thing going on here as we do right here, we know this is 90, this is 90, and this is 90. Finally, again, due to the fact that we built this shape by making 4 copies of a triangle, this is the third side of our triangle, this is the third side of our triangle, and so are these. Again, we're dealing with a box which has 90 degree angles in all 4 of its corners, and the same length on each and every one of its sides, the definition of a square. So let's call this inner box square number 2. And then finally, let's introduce T to be the name of our triangle. The last thing we're going to tackle is, what is the area of square 2? And in order to do that, we have to find the relationship between square 2 and the other shapes that we've created. You can tell from looking at this box that the area of square 2 is going to be the area of this outer box, square 1, minus the area of each of these triangles. since they all have the same area, square 2's area, is given by square 1's area minus 4 times the area of the triangle that we created. But what is the area of square 1? Well, the area of a square is called the side length x. The area of a square is just given by the length of one of its sides squared. And the side length of S1 is just given by a plus b. So S1 is a plus b squared. All right? What about the area of this triangle? Well, we can think of every triangle as really just being a rectangle that was sliced in half down one of its diagonals. Here's A and here's B. We know the area of this rectangle is just A times B. And so the area of half of it, in other words, this triangle that we've created, is just going to be A times B over 2. And that's what we're going to use over here. Minus 4 times AB over 2. All right? Now let's expand these two terms out. We know that A plus B squared is given by A squared plus 2AB plus B squared. This 4 and this 2 are going to cancel each other out because 4 divided by 2 is just going to give us a 2 on the outside. And so ultimately we have a minus 2AB over here. These two terms are identical, except one is being added and the other is being subtracted. So they cancel each other out. And the area of S2 is ultimately going to be A squared plus B squared. And the final thing that we're going to talk about with this box is, let's talk about this third side that we have yet to name. This third side is one of the sides that builds square S2. We know that the area of a square is just given by the length of one of its sides squared. So let's call this side length C. The area of S2 is the side length C squared. But look what we have here then. This tells us C squared equals A squared plus B squared. And if we just look at our original triangle in isolation, without considering this fancy box, we see, oh, mixed up the sides. We see that what we've really written, what we've really just proven, is the Pythagorean theorem.